So last week we focused on one specific type of energy called kinetic energy, and we showed its formula and used its formula for a few things. In the previous lesson, you learned a description of a whole bunch of other types of energy, but there's only one of them that we're really going to focus on the formula for as well, in addition to the kinetic energy, and that's gravitational potential energy. So this is the formula for gravitational potential energy. Remember that this type of energy is described as the energy associated to an object's height relative to some reference level. So in terms of, the formula is pretty straightforward. It's just three variables multiplied together. And what those variables mean, as well as their SI units, are written here. So capital U stands for potential energy. And if I want to specify which kind of potential energy, I'll write a subscript. So for the case of gravitational potential energy, I use the subscript of G. Now I probably won't be using U sub G in grade 11 because, like I said, this is the only potential energy formula we'll do in grade 11. But in grade 12, you'll have different formulas for different ones, so you'll need subscripts. But for this year, you'll just see capital U standing for gravitational potential energy. The SI units for energy are joules. So just like kinetic energy is measured in joules and work is also measured in joules, gravitational potential energy is measured in joules, and it is a scalar quantity. So we do not add a direction for the gravitational potential energy. The M in the formula stands for mass. The units have to be kilograms in order to use this formula. So if it's given in grams or anything else, you have to convert it to kilograms first. G, we're familiar with as 9.8 for the value for Earth, at least. That's the gravitational field strength in newtons per kilogram. And then H, here's where it gets kind of tricky. You have to pay careful attention. H stands for the elevation or the height of the object with the SI units of meters. And in red here, this is the important part. This is the height of the object in relation to a specified reference height. In each problem, you must specify what you're using for the reference height and stick with your choice for the entire problem. So in this picture of a roller coaster here, the first person, how high is that person? What's the height of this person? Well, in order to answer that question, the reader needs to know where you're measuring all the heights from. Like, are we talking about the height compared to the ground here? Or are we talking about the height compared to this end of the track here? Or are we talking about the height compared to the top of the roller coaster here? In which case the height of this object would be 0. Okay, so where are we measuring the height from? That matters a lot. Think of an apartment building. Let's say you're on the 5th floor of an apartment building and you've got a physics textbook in your room on the 5th floor of an apartment building. Well, how high is the textbook? Well, you have to ask, are we asking how high is it compared to the street? So that's like 5 floors up. Or are we talking about how high is it compared to the floor of your room? In which case it would not be that high at all. All right. One more thing, heights could be negative. Right? Heights could be negative. So let's say I've got my physics textbook right here, and I can ask, how high is this physics textbook compared to the ceiling? Right? Compared to the ceiling. Well, if the ceiling's up there, then this textbook, I would say, would have a height of approximately negative 2 meters because it's 2 meters below my reference value. Okay, so it's really important that you specify where you are measuring your heights from when you solve problems. So I'll just have 2 problems as an example. Here's number 1. A falling 100-gram apple is 1 meter above the ground and 2 meters below the branch from which it fell. how much gravitational potential energy does the apple have? So we're going to use the formula U equals mgh, but before we plug in the value for height h, we have to know where we're measuring the height from. So in this slide, I'm actually going to show you 3 different solutions. All of them are correct. And the final answers are different, but they're all going to be correct. Here's the first solution. So in solution 1, we choose the ground as the reference height. Okay, so we're going to measure all the heights with respect to the ground. So when I list out my variables, the mass is 0.1 kilograms because I had to convert 100 grams to kilograms. The G value is 9.8 newtons per kilogram, but the height is going to be positive 1 meter. If the ground's the reference height, then yeah, this apple is at a height of positive 1 meter. And then you use the formula U equals m times g times h. So I multiply these 3 numbers together, resulting in 0.98 joules. A second solution, that's a different answer, but also correct. What if we choose the apple's current height as the reference height? So that's an interesting and kind of clever and smart choice to do. So instead of measuring heights from the ground, the solution number 2 is measuring heights from exactly where the apple is. It's like an imaginary horizontal line there, then that counts as a height of 0. So when I list the variables, mass is still the same, g is still 9.8, but now the height is 0 meters. And then when I multiply something times 0, m times g times h, anything times 0 is 0 joules. And that would be the right answer if I chose the apple's current height as the reference height. And then a third and final option, well, not a final option, but the final one for this slide, is what if I choose the branch that it fell from as the reference height? Okay, so there's a branch here. What if I decide to measure the heights relative to this branch? Well, where's the apple? The apple is 2 meters below this branch, so I would actually list that as a h equals negative 2 meters, since it's below the branch. Mass is the same, g is the same, U equals m times g times h, so when I multiply these 3 together, I get negative 1.96 joules to 2 significant figures. And in this case, the answer is a negative amount of gravitational potential energy, which is allowed. Okay, negative values are allowed for gravitational potential energy. That just means that the object has a height that's below the reference height that was chosen. So in any problem you do with gravitational potential energy involved, you have to tell the reader where your reference height is and stick with that for the whole problem. Okay, you can't switch it halfway through the problem. And now one more example. So I need to make another point here. The value for U, for gravitational potential energy, it can be positive or it can be 0 or it can be negative, and they can all be the right answer, just depending on which reference height was chosen. However, a change in U will always be the same. It will not depend on what reference height you choose. So in this example here, Mr. Tang is 70 kilograms and begins by hanging 2 meters above the ground on a rope. He then climbs the rope to reach a point 6 meters above the ground. Determine his change in gravitational potential energy. So I started with some kind of gravitational potential energy, or U, and then I ended with a different amount of U. So there was a change there. How much was my change in U? And once again, I'll calculate this 2 different ways with 2 different reference heights. But this time I'll show you that no matter what reference height, either of the 2 reference height I chose, the answer is the same. So here's my first option. I could choose, I can choose the ground as the reference height. So if I choose the ground as the reference height and I list out my values, the mass was 70 kilograms, the G value is 9.8 for Earth. With the ground as the reference height, my starting height, H1, was 2 meters. And then my ending height, H2, was 6 meters. So then when I calculate my change in U, that would be represented by delta U. Delta, anything, is final minus initial. So I change delta U to U2 minus U1. The formula for U is mgh, so it's mgh2 minus mgh1. And then I plug in all the values that I had in that list there. And you can see I eventually end up with 2,744 joules. That would be 2 significant digits. All right, so that's my change in gravitational potential energy. It's saying that I've increased my amount of gravitational potential joules by 2,744. And that increase should be the same no matter where I chose the reference height. So I'm going to show you solution 2, where I used the highest point as the reference height. I used the highest point as the reference height. So the mass is still 70 kilograms, G is still 9.8 newtons per kilogram. Now my starting height, if I chose the highest point as my reference height, then I actually started at -4 meters high. Okay, I'll give you a second to think about that math there, coming from this 2 and the 6. So if the reference height is at the top of the rope, I started 4 meters below that. So my H1 is -4 meters. My final height would be 0 meters. It would be exactly at the top of the rope where I ended. So my ending height would be 0 meters. So if I go on to calculate my change in U again, so my delta U is U2 minus U1, mgh2 minus mgh1. Fill in the values, and the first part's nice because it's 0. Then I end up getting 0 minus negative 2,744, which equals positive 2,744, which is the exact same answer I got as before when I chose the ground as a reference height. Okay, so the point is that if I change my height, then the change in U is the same, no matter how I calculate it. Okay, if I got higher, my U is going to get bigger. I'm going to get more joules. On the flip side, if I fall down, if I get to a lower elevation, then my number of joules for gravitational potential is going to go down, no matter what. All right, so there's an introduction to gravitational potential energy. There's 2 things for you to do. Google form with just 3 questions on it to test these concepts, and then a few calculations to do on a Google Doc, which might be kind of interesting actually when you see the answers to those questions.